Hello and welcome to this last video in this course. In this course, I'm going to finish chapter 3 by explaining the residue theorem. Okay, so what is the residue of a holomorphic function on a punctured disk? If you have a holomorphic function on a punctured disk, which is in our definition is an annulus actually. So annulus, punctured disk, same thing. We know from the previous video that we can expand f in a Laurent series, okay? Because there may be a problem at A. Now, the coefficient of 1 over z minus A has a particular role to play, and it's called the residue. So A minus 1, the coefficient. Why is it so important, actually? Because we shall see that when we integrate, let us say, over a loop, all the terms in the sums possess an antiderivative except 1 over z minus A. So all terms vanish except this one. So this is what's called, and we encountered this situation before, actually. So the coefficient of 1 over z minus A in the Laurent series is called the residue. Now, this is the definition. Now, later we shall see some methods for computing the residue. But the definition, when you go back to the Laurent series, if you can expand f in the Laurent series, then you find everything, actually. You find the residue, the nature of the singularity, and so on. Okay, so what is the residue theorem? If omega is a simply connected subset of C, and we have a finite set Z1, Z2, Zk that I call S, finite set of subset of omega. And we have a holomorphic function on omega without S. So Z1, Z2, Zk are the singularities of F. Okay? If gamma is a piecewise smooth loop in omega, not containing the Zks, the Zjs, then the integral over gamma of F is 2 pi I times the sum of the residues multiplied by the index of gamma with respect to, by the way, this is Zm, it's an error here. It's Zm here. Okay, so let us prove this theorem. For each S in the singular set, it's a finite set, let F sub S denote the singular part of F. Okay, because we can expand F on a neighborhood of each S as a Laurent series. So Fs is the singular part. Okay? Then Fs is holomorphic on C without S, right? Because it's a series of singular. The only problem is at 0, actually, as we know. Now, when I subtract from F the sum of all singular parts, so I remove all singularities, I obtain a holomorphic function. Okay? And since omega is simply connected, gamma is homotopic to a point. Is omega homotopic to a point? Therefore, I can apply Cauchy's theorem. So the integral over gamma of G is 0. And if I go back to the definition of G and I split my integral into 2 parts, the integral of F over gamma is equal to the sum of the integrals of Fs. Okay? So this is where the sum comes from. So I need just to now to prove what? That the integral of Fs is 2 pi I times the index times the residue. Okay, so let us fix one S, one singular point, and compute the integral over gamma of Fs. Okay, we know that Fs is, since it's the singular part about S, it can be written in this way. And we know from the theory of Laurent series that convergence happens inside any compact set of the annulus. Okay, so in particular, we have a uniform convergence on gamma, because gamma is a compact set of C without S. So we can integrate term by term. So as I said, when we integrate term by term, all terms possess an antiderivative except when n equal 1. Okay? This is why it's called the residue. So when I integrate, the only surviving term is actually 2 pi I times, so the integral of 1 over z minus a. So here it is. So the integral of fs, so everything vanished except the integral of b minus 1 over z minus s. And this has a name. It's 2 pi I times the index of gamma with respect to s. Right? So it's 2 pi I times the residue times the index. Okay? And then it's enough just to sum everything. So it's very easy. And we encountered this idea before. Okay? So this finishes the proof of the residue theorem. Not so difficult. Now, of course, you can modify a little bit the assumptions. Instead of assuming that omega is simply connected, you may assume that omega is any open set, and the loop is homotopic to a point. Just another way of formulating the same thing, actually. So it's like when we formulated Cauchy's integral formula, because it's the same ideas. Okay? Now let us see some applications, how the residue theorem is useful to compute some improper integrals. Okay, but before doing that, let me give you some practical methods for computing the residue, other than the one involving going back to the Laurent series, because when we expand f in a Laurent series, you automatically have the coefficient of 1 over z minus z0. Okay. Now, there are when z0 is a pole, actually, there are some methods, some algebraic methods, actually. So I'll present one of them. If z0 is a simple pole, then we just multiply f by z minus z0 and we eliminate the singularity, and the limit is actually the residue. Okay, and this is easy to prove because we know that if z0 is a simple pole, then f can be written as the ratio of a holomorphic function over z minus z0, because the degree is 1 here, because it's simple. So when we multiply by z minus z0, we eliminate the singularity and we get g of z. So, and this tends to g of z0 as z tends to. So this is, yeah. So the residue is just the value of g at z0. So this is easy. Now, as a consequence, if my f is the ratio of two holomorphic functions, and z0 is a simple 0 of q, so I can factor q by z minus z0, then the residue is just p of z0 over q prime of z0, just a simple consequence. So for example, if we take f of z to be e minus z squared over z minus 1, okay, let us copy. There are two problems here. There's the residue at 0 and the residue at 1. Okay, now if you look at the denominator, it's something of the form q of z, and z equals 0 is a simple 0, and similar for 1 actually. But if you concentrate on 0, just we can either multiply by z and go to the limit, or actually just apply this rule. So it's p of z0 over z minus 1, and this is minus 1. Okay, so you can either apply this or apply the previous one. Same thing. You'll check that it's minus 1. Okay, this is if you don't want to expand in the Laurent series. But if you expand in the Laurent series about 0, then you get precisely that the coefficient of 1 over z will be minus 1. Now, what if z0 is a pole of order p? Then we have to multiply by z minus z0 to p and then differentiate. So the rule is that when z0 is a pole of order p, then you have to multiply by z minus z0p and differentiate p minus 1 times. You'll get the residue. And I'll give an illustration now. For example, if you take 1 over z squared z minus 1, we see that z0 is a pole of order 2 because I can expand this in a geometric series and about 0, and then I divide by z squared. So, of course, you always have the option of expanding in a Laurent series if you like, but if you want to apply this formula, here p equal 2, so we multiply by z2 and then differentiate 1 times because p equal 2. So we differentiate p minus 1 times and you get minus 1. Okay? And another method is actually, as I said, is to expand in a geometric series z minus 1 about 0, and then divide by z squared. You get precisely the coefficient of 1 over z will be precisely minus 1. Okay. Yeah, this is what I was saying. So you see that the coefficient of 1 over z is minus 1. Now, if Z0 is an essential singularity, there is no formula for the residue. So we have to go back to the Laurent series and see what is the coefficient of 1 over Z minus Z0. Okay. The Laurent series contains so many information. Okay, it contains you can compute the residue. You know the nature of the singularity. Is it removable or a pole or an essential singularity? Okay. Now, let me illustrate the residue theorem together with these rules for computing the residue to compute a complex integral, the integral of tangent z. Tangent is just sine over cosine, as you know, over the circle of radius 2, positively oriented. Okay. We have to know when we want to integrate a complex variable on a loop, we must see what are the singularities. The singularities of tangent are actually the zeros of cosine, which are, as we know, pi over 2 plus n pi. Now, usually, only the residue, the singularities inside the circle influence the result, because for the singularities outside, their index is 0, so they don't contribute to the result. So if you look at the circle of center 0 and radius 2, you will see that only pi over 2 and minus pi over 2 are inside. Okay? So actually here, you can take omega, any band containing the circle. Okay, for example, you can take minus pi, because pi is bigger than 2. So this is, of course, a convex domain, so it's simply connected. Okay? So on this domain, actually, f has two singularities, which are pi over 2 and minus pi over 2. So as I said, omega is an open convex set and therefore simply connected. It contains the circle, and f is holomorphic on omega without minus pi over 2 pi over 2. So we can apply, as in the case of Cauchy's integral form, we can apply the residue theorem, and this gives me 2 pi I times the sum of the residues multiplied by the indices. Now, as usual, as most often, the indices are 1 because gamma is positively oriented and the singularity is inside. So pi over 2 and minus pi over 2 as in. So you can just draw a picture if you like. Okay, so in order to, so this is 1, this is 1, just have to compute the residue. Now, if we want to compute the residue, we have two options. Either we expand f in the vicinity of pi over 2, so in the punctured disk, let us say, of center pi over 2 and radius, so the radius pi will be actually, because the distance is the next singularity. You can do that. Or you apply the rules that I explained, because we know here that pi over 2 is a simple pole, actually, of course, of 1 over cosine. So this is something of the form p over q. Since it's a simple pole, so if you apply the formula, you get sine pi over 2 over cosine prime pi over 2, and this is minus 1. Okay. And similar for minus pi over 2, we get minus 1 as well. So when I do everything, I get minus 4 pi I. Okay. Now, this is a shortcut, actually, if you like, but because expanding in the Laurent series could sometimes be a little bit tedious. Okay, so these are shortcuts to compute the residue. Okay, so this is the first illustration. And in general, the residue theorem used properly can permits us to compute integrals of very general form. So we can have, so here we took tangent, which is sine over cosine, but we can take any rational function of sine and cosine. So polynomial over polynomial in sine and cosine. I'll illustrate that. We can use the residue theorem to compute improper integrals of this form, a rational function times cosine, and the rational function times sine, from minus infinity to infinity. And we can also use this to compute the integral of a rational function from minus infinity to infinity. Okay. So now I will just give an example for computing an integral of type A. And in the exercises, we will explore methods. So we'll see how to apply the residue theorem to compute integrals of type B and C. Okay, but it's the same strategy actually. Okay, so this is the general method. If you want to compute an integral of this type, so what we do is we let Z be EIT. Then if you use Euler formulas, we get cosine is 1/2 EIT plus E minus IT. So it can be written as Z plus 1 over Z. And sine t can be written as 1 over 2i Z minus 1 over Z. Okay, and so when we replace sine and cosine by their values, we get a rational function actually of these of Z minus 1 over Z and Z plus 1 over Z. So we get an algebraic expression. So if we compute this usually by using the residue theorem, and we deduce the value of the real integral. Okay, this is the general strategy. Okay, so let us give an example. For example, compute the integral from 0 to 2 pi of 1 over 2 minus cosine t. Okay, how to invent or how to find the function of a complex variable that we need to integrate. So we follow the method, the general methodology. We replace cosine by Z plus 1 over Z over 2. So, but we need to divide by IZ, okay? Because when we do the change of variables, you must multiply then by the derivative, so IEIT, okay? So if we do these computations, we'll find 2i over this polynomial. And how to integrate that? We need to factor it, okay? So we find two roots here, two real roots, which are 2 plus radical 3 and 2 minus radical 3. And we need to integrate over the unit circle, right? So we look at the residues. So only 2 minus radical 3 is inside. The other one is outside. But in order to apply the residue theorem properly, we consider a convex set containing the circle, but not containing 2 plus radical 3. So this is just a half plane. So just draw a picture actually. So if omega is convex, then it's simply connected, so we can apply the theorem. It's convex set containing the loop, and F is holomorphic on omega except at this point. So the residue theorem tells me that it's 2 pi I times the index of gamma with respect to 2 minus radical 3, the singularity inside, times the residue. Okay, this is the residue theorem. And once again, the index here is 1 because it's simply loop positively oriented, containing the singularity inside. And the residue, because it's a simple pole actually, so just multiply F by Z minus 2 minus radical 3. And when we simplify, and then we let Z tend to 2 minus radical 3, we get minus I over radical 3. So put instead of Z 2 minus radical 3. So putting everything together, we get I equal 2 pi over radical 3. Note that here in this case, the integral the value should be real because it's the integral of a real function. Okay. Otherwise, it's a sign that you made an error in the computations if you get the complex value. Okay. Now, of course, in the simple case, we can also apply Cauchy's integral formula. Okay, we are not obliged to use the residue. When there is only one singularity, as a general rule, when there is only one singularity inside the loop, we may use Cauchy's integral formula. But the residue theorem is convenient when you have several singularities inside. Okay. And we shall explore more examples in the exercise. But this is the general strategy, actually. Okay. So this concludes the video and concludes the course. That's it for this course. Next week, I'm going to solve the exercises, and we may use Zoom to answer your questions. So prepare well your questions, and if you like, we can also meet at the university if you are not far. So thank you for your attention, and see you soon.